Nobody in this room has ever felt gravity. Not once. Not a single day of your life. You feel the floor pushing up against the soles of your feet. You feel the chair pressing into your back. You feel the blood pooling slightly toward your heels when you stand. But gravity itself, the force, you have never felt it, and you never will, because gravity doesn't push or pull you in any way that your nervous system can detect. Gravity is the shape of space. And if that sentence made you uncomfortable, good. Stay with me, because in about 10 minutes, I'm going to ask you to imagine something that, if you think about it honestly, is one of the most catastrophic scenarios a physicist can construct. And I'm going to do it using nothing more than what you already know. If we're willing to follow the logic wherever it leads, the question is this: what happens if gravity turns off? Not forever, not for a year, for 5 seconds, 98 feet of free fall. That's what 5 seconds of no gravity gets you near the surface of the Earth if we ignore air resistance, if we treat this as a clean thought experiment. 5 seconds, less time than it takes to read this sentence aloud. And I want you to understand, before we go any further, that the answer is not things float around for a moment and then come back down. The answer is civilizational destruction on a scale that dwarfs every natural disaster in recorded history. And I don't say that to be dramatic. I say it because it's physics, and physics doesn't negotiate. But here's the thing: I want to start with the thing that I think is actually more interesting than the disaster scenario and more important. Before we can ask what happens when gravity disappears, we have to be honest about what gravity actually is. Because most people, including a lot of people who should know better, are still carrying around Isaac Newton's picture of gravity in their heads. They think of it as a force, a tug, an invisible rope connecting massive objects across empty space. And Newton himself knew that picture was wrong, or at least incomplete. He said so. He wrote in the Principia that he had been unable to discover the cause of those properties of gravity from phenomena, and he wasn't going to feign hypotheses. That's a 300-year-old confession from the greatest physicist of his age, that he didn't know why gravity worked, only that it did, and that the equations described it with extraordinary precision. 230 years later, a 26-year-old patent clerk in Bern had an idea. He called it the happiest thought of his life. And the thought was this: a man falling freely through space feels no gravity at all. If you are in free fall, if there is nothing pressing on you, nothing pushing back, you are locally in an inertial frame. You are weightless. You feel nothing. And Einstein asked, what if that's not a trick? What if weightlessness during free fall isn't a coincidence, isn't an artifact of the math? What if it's telling us something deep about what gravity actually is? What it's telling us is that gravity is not a force in the same sense that electromagnetism is a force. Gravity is geometry. It is the curvature of space-time caused by the presence of mass and energy. Objects don't fall toward the Earth because something is pulling them. They fall because the straightest possible path through curved space-time, what we call a geodesic, happens to be a path that curves toward the Earth. You are always moving in a straight line through space-time. The Earth is just warping the space-time around it so that the straight line happens to point toward the ground. I know what some of you are thinking. You're thinking, fine, but that's just a different way of describing the same thing. It predicts the same orbits, the same trajectories, the same falling apple. And you're almost right, almost. The difference between Newton and Einstein isn't just philosophical, it has measurable, observable consequences. The bending of light around the sun, the precession of Mercury's orbit, gravitational time dilation, the fact that clocks tick slower in stronger gravitational fields, which is not a metaphor. It is a measurable fact that your GPS system corrects for every single day, or it would accumulate errors of kilometers within hours. These are not Newtonian predictions. They are Einstein's, and they are right. And Newton's are wrong in exactly the cases where Einstein's are different. Now, here is where it gets strange. If gravity is the curvature of space-time, then asking what happens if gravity suddenly disappears is not asking what happens if someone turns off an invisible force field. It is asking what happens if space-time itself suddenly snaps back to being flat. And that question, that specific formulation, is one that general relativity has a very pointed answer to. And the answer is it can't. Not like that. Not instantaneously. Not everywhere at once. Here is why. In Einstein's theory, changes in the gravitational field, changes in the curvature of space-time propagate at the speed of light. They travel as gravitational waves. We know this because we detected them for the first time in September 2015, when the LIGO interferometers in Louisiana and Washington state picked up a ripple in space-time smaller than 1/10,000th the diameter of a proton, a ripple produced by two black holes merging a billion light years away. That detection was one of the most extraordinary moments in the history of science, and it confirmed something Einstein had predicted a century earlier. Disturbances in spacetime travel outward from their source at exactly 299,792,458 meters per second. Not faster, not slower, not instantaneously. So the scenario gravity disappears everywhere on Earth simultaneously is not just physically catastrophic. It is physically impossible under general relativity. It requires either that information travels faster than light, which relativity forbids, or that gravity is not what relativity says it is. But let's put that constraint aside for the sake of the thought experiment. Let's say by some mechanism we don't understand, gravity simply vanishes, globally, instantly, for 5 seconds. What actually happens? Let me build this from the ground up, and I mean that almost literally. The first thing you have to understand is what gravity is doing to the Earth right now, in this moment, as you sit here. It is not merely holding you to the floor. It is holding the floor together. It is holding the building together. It is holding the mountain ranges together. It is holding the oceans and their basins. It is maintaining the spherical shape of the planet itself, because that shape is not a coincidence. It is the result of billions of years of self-gravitating material finding the lowest energy configuration, which is a sphere, and below your feet, in the mantle, there are rocks under pressures of hundreds of thousands of atmospheres, compressed by the weight of everything above them, kept in their semi-molten, flowing state, partly by that pressure. Gravity is not just holding things down. It is the dominant force shaping the structure of the entire planet. Now take it away, all of it, instantly. Within the first second, every object, not mechanically attached to something else, begins to drift. You sitting in your chair drift upward, or rather the chair drifts away from you because there's no longer any force pressing you together. The atmosphere, which is held against the planet entirely by gravity, in the same way the oceans begins to expand outward, not slowly. The outermost layers of the atmosphere, where the density is already low, begin to move immediately. The denser lower atmosphere takes a fraction of a second longer to respond, because the air pressure at sea level is itself a consequence of the weight of all the air above it. And without gravity, there is no weight. And without weight, there is no pressure differential. And without that pressure differential, the air begins to expand freely in all directions, including upward and outward into space. In the oceans, the situation is different, but equally catastrophic. Water is nearly incompressible, but it is not being held in the ocean basins by the basins. It is being held there by gravity. The basin is just a shape in rock. It has no walls above sea level on most of the planet. Without gravity, the ocean surface is no longer a surface. It is a boundary condition that has just ceased to exist. The top layers of the ocean, hundreds of meters of water, begin to move upward and outward as a coherent mass. Not as droplets, not as mist, but as enormous sheets and blobs of liquid water, kilometers across, lifting free of the rock below. And beneath all of this here is the thing that I find most astonishing and most underappreciated. In any casual treatment of this scenario, the Earth's interior begins to respond. The mantle is under enormous pressure. The outer core, liquid iron, is under even more. Remove the gravitational compression, And you do not simply depressurize the planet the way you'd open a carbonated drink. You initiate a process by which the internal pressure, which was balanced by the weight of overlying material, now has nothing to push against. The material begins to expand. The mantle rock, which was behaving as a viscous fluid on geological timescales, but as a solid on human timescales, is subject to sudden pressure relief on a scale that dwarfs any volcanic eruption in the history of the planet. In 5 seconds, the effect doesn't have time to propagate from the deep interior to the surface. Seismic waves travel at roughly 10 kilometers per second, and the Earth's radius is about 6,400 kilometers. So you're looking at about 10 minutes before a disturbance from the core reaches the surface. 5 seconds of no gravity doesn't unravel the deep interior, but the surface, the crust, the oceans, the atmosphere, that's a different story. Now, here is where it gets strange in a different way, a more personal way. For me, I have spent a significant portion of my professional life thinking about what happens at the boundaries of physical systems when the rules change. Not gravity specifically, but the general question, what does a system do when a constraint is suddenly removed or suddenly imposed? And for a long time, I thought the interesting answer to this thought experiment was the physical catastrophe, the water, the air, the structural failures. But the more I sat with it, and I've been sitting with versions of this question since graduate school, the more I realized the most interesting answer is not what happens in the 5 seconds. It's what happens in the first millisecond after gravity returns. Because everything that drifted upward comes back down, not gradually, all at once. With the full force of Earth's gravity, 9.8 meters per second squared, acting on objects that have been moving away from the surface for 5 full seconds at whatever velocity they had accumulated, near the surface in that 5 seconds, you'd have risen about a meter if you started from rest, but you'd be moving at nearly 50 meters per second by the time gravity turned off. And when it came back, you'd be about 12 meters off the ground and moving upward at 49 meters per second. You would then decelerate, arc, and come back down, hitting the ground at 49 meters per second, which is about 110 miles per hour. That is the terminal velocity of a human body in free fall, experienced not as a gradual buildup over hundreds of meters, but as a sudden collision with the floor. Every person on Earth who was standing, sitting, or lying down would become a projectile. Every car on every road, every airplane, though, pilots would have had 5 seconds to react, which is both more and less than it sounds, depending on what they were doing. Every building would have experienced 5 seconds during which the loads it was designed to carry, loads that assumed downward acting gravity, simply vanished. And structural members that were in compression are now unloaded, and the building has begun to move. And when gravity returns, it returns to a structure that is no longer in its designed configuration. And the water is what I keep coming back to. Vast sheets of ocean water lifted hundreds of meters off the seafloor in some places, because remember, the ocean is on average 3,800 meters deep. And in 5 seconds, you don't lift all of that. But you absolutely lift the top layer, and that top layer has mass. And when gravity returns, it falls. It does not gently settle. It hits whatever is below it with the kinetic energy of an object that has been in free fall. In deep ocean, it hits more water, and you get pressure pulses propagating outward that would make the 2004 Indian Ocean tsunami look like a ripple in a bathtub. In shallow coastal areas, it hits the seafloor and the coastline and every coastal city on Earth simultaneously. I want to be precise here, because imprecision is a form of dishonesty. The energy in even a modest column of ocean water, say 50 meters deep, over an area of a few square kilometers falling back from 50 meters of altitude, is on the order of 10 to the 13th joules. That is roughly equivalent to a 2-kiloton nuclear detonation. And this is not happening in one place. It is happening simultaneously across every ocean on Earth. The re-impact of the displaced ocean water globally is an event for which we do not have an adequate vocabulary outside of planetary science. It is a mass extinction event, not a possible one, a certain one. I want to stop for a moment and be honest with you about something because I think intellectual honesty is more interesting than a clean narrative. The scenario we're discussing, gravity vanishing instantaneously everywhere, is not just physically catastrophic. As I mentioned earlier, it is physically impossible, as stated within the framework of general relativity. The speed at which gravitational effects propagate is the speed of light, and the sun is 8 light minutes away. If the sun's mass suddenly vanished, we would not feel the loss of its gravitational pull for 8 minutes. We would continue orbiting, blissfully ignorant, for 8 minutes, and then the Earth would fly off in a straight line into the void, and 8 minutes later, the light from the sun would stop arriving. In that order. Gravity first, light second, by no time at all, because they travel at the same speed. I find that fact wonderful and a little eerie. There is no gravitational action at a distance that is instantaneous. Every gravitational interaction you've ever experienced, the Earth holding you down, the moon raising the tides, is mediated by the curvature of space-time, and that curvature propagates at a finite speed. The moon's gravitational field that you're sitting in right now is not the moon's gravitational field as it is now. It is the moon's gravitational field as it was 1.3 seconds ago. The sun's gravity that keeps us in orbit is the sun's gravity as it was 8 minutes ago. We are always living in the gravitational past, always responding to a universe that is slightly behind where it actually is. That is not metaphor, that is not poetry. That is general relativity, and it is as hard and precise as anything in science. So where does our thought experiment actually live? If not in general relativity, where? It lives in the category of what physicists sometimes call background-dependent perturbation scenarios, where you change one parameter of reality and ask what follows, while holding everything else fixed. This is a legitimate and useful exercise, even when the scenario itself is unphysical. Thought experiments are the laboratory of theoretical physics. Einstein didn't have a spaceship. He had his imagination and the willingness to follow the logic. The question, what would I see if I rode alongside a beam of light, is also unphysical. You can't do it. But following that question led to special relativity. The question, what would the universe look like if it were a billion times smaller, is also unphysical in the sense that we can't observe it directly. But following that question through thermodynamics and quantum field theory led to our understanding of the Big Bang. Thought experiments are not idle speculation. They are the sharpest tool in a physicist's kit, and if you're embarrassed by them, you don't understand where the best physics comes from. So we'll keep going. Not because this scenario could happen, but because it illuminates things that are real. Let me tell you about a conversation I had once, and I'm not going to say with whom, because the point isn't the personality. The point is the idea where someone pushed back on me during a lecture and said, essentially, isn't this all just a physics problem? Gravity comes back, things fall, it's messy, people die. What's philosophically interesting about it? And I said, everything. Everything is philosophically interesting about it. Here's what I mean. The scenario of gravity disappearing for 5 seconds is a probe. It's a way of asking, what exactly is gravity doing at every moment of every day that we don't notice because it's always there? We don't notice gravity the way fish don't notice water, not because it's invisible, but because it's constant. It's the baseline of our experience. Every structure ever built by human hands has been built in the presence of Earth's gravity and has been designed to function in that gravity and has been optimized over thousands of years of trial and error, with the spectacular and permanent losses of those trials built into the design decisions that survived. We are so embedded in gravity that we have to think very carefully, even to ask what it would mean for it to be absent. And when you do think carefully, when you actually trace through what gravity is doing to every system on Earth at every moment, you realize that gravity is not just a force acting on your body. It is a structuring principle of the entire biosphere. Every organism on Earth has evolved in 1G. Your cardiovascular system is built around it. Your heart is sized to pump blood against a 1G gradient. Your skeletal system is built around it. Your vestibular system The tiny organs in your inner ear that tell you which way is down are calibrated to it. Astronauts returning from long duration spaceflight have to be carried off the spacecraft. They can't walk. After 6 months in microgravity, the human body has partially unlearned how to operate in a gravitational field. The muscles have atrophied, the bones have lost density, the cardiovascular system has remodeled. The body is not a fixed thing. It is a dynamic equilibrium with its environment, and gravity is a fundamental part of that environment. And it's not just animals. Plants orient themselves through gravity. The phenomenon is called gravitropism, and it's as fundamental to plant physiology as photosynthesis. Roots grow downward because of gravity. Shoots grow upward against it. The internal signaling molecules that tell a plant cell which way to grow are distributed asymmetrically by the pull of gravity. In 5 seconds, nothing dramatic happens to a tree's root system. But in zero gravity on timescales of weeks or months, plant growth becomes chaotic. Roots grow in spirals, shoots twist randomly. Gravity for a plant is not an obstacle, it is a compass. And the most profound version of this point is the one that operates at the planetary and solar system scale. Every orbit is gravity. The moon's orbit around the Earth's orbit around the sun's path through the Milky Way, the Milky Way's interaction with Andromeda. Remove gravity, even for 5 seconds, and every one of these systems shifts. Not much. 5 seconds is nothing on orbital timescales, but not zero. The moon, in 5 seconds of no gravity, travels in a straight line at roughly 1 kilometer per second, displacing itself by about 5 kilometers from where it would have been. When gravity returns, it is now in a slightly different position than it would otherwise occupy. The orbital perturbation is tiny, and orbital mechanics has remarkable stability over short timescales, so the moon does not fly away. But the principle holds. 5 seconds of no gravity is not 5 seconds of no consequence. It is 5 seconds of change to every gravitationally bound system in the universe simultaneously, because the scenario as we've posed it is global, or at least applies to the Earth and its environment. Now, here is where it gets strange in the most fundamental way I know. You might be wondering, some of you have probably been wondering since I started, what would actually cause gravity to disappear? What mechanism could possibly produce such a thing? And the honest answer within our current physics is nothing. There is no known mechanism. Gravity, in general relativity, is not a field you can turn off like an electromagnetic field, because in principle you can shield an electric charge. You cannot shield gravity. You cannot make a gravitational insulator. Every mass curves space-time, and there is no way to prevent it, and there is no material that blocks it. Gravity passes through everything, always, without attenuation. When the LIGO detectors picked up the gravitational wave from those merging black holes, the wave passed through the entire planet Earth without losing a measurable fraction of its energy. That is how fundamentally non-shieldable gravity is. But here is the thing that keeps me genuinely awake at night in the most productive sense. We do not have a quantum theory of gravity. We have general relativity, which is a classical field theory, exquisitely accurate but fundamentally incompatible at the mathematical level with quantum mechanics. We have the standard model of particle physics, which accounts for electromagnetism, the strong nuclear force, and the weak nuclear force in terms of quantum fields and their associated particles, photons, gluons, W and Z bosons. But we do not have a graviton. We have not observed the quantum of the gravitational field. We do not know if such a thing exists in a form consistent with a renormalizable quantum field theory. Every serious attempt to quantize gravity in a straightforward way produces infinities that cannot be absorbed, divergences that signal a breakdown of the theory, not a solution. String theory is one attempt to resolve this. Loop quantum gravity is another. There are others. All of them are mathematically sophisticated. Some of them are deeply beautiful, and none of them have made a prediction that we've been able to test. We are in the extraordinary position of having a theory general relativity that is one of the most precisely tested theories in all of science, predicting things like the orbital decay of binary pulsars to 1 part in 10 to the 14th, and simultaneously knowing with certainty that that theory is incomplete. It is not the final word. It cannot be, because it is incompatible with the other theory that is also one of the most precisely tested in all of science, which is quantum mechanics. And two theories that are both right, both tested, and mutually incompatible cannot both be the complete story. One of them, probably both of them, are approximations to something deeper that we do not yet have. And the question of what gravity actually is, at the most fundamental level, whether it emerges from some deeper structure, whether space-time itself is a kind of thermodynamic average over some underlying quantum degrees of freedom, that question is alive. It is not settled. It is the single most important unsolved problem in theoretical physics, and anyone who tells you otherwise is either working on something else or not being straight with you. I want to close with something that I think is the deepest lesson of this thought experiment, deeper than the physics of what would happen, deeper than the philosophical point about how embedded we are in gravity as a condition of existence. When we do a thought experiment like this one, when we imagine a fundamental constant of nature or a fundamental force being suddenly arbitrarily changed, we are implicitly asking a question about the universe that is not yet answered. Why are the laws of physics the way they are? Why is the gravitational constant the value it is? Why does gravity obey an inverse square law in 3 spatial dimensions? Why is gravity attractive rather than repulsive? And why is it so absurdly, comically weak compared to the other forces? This last point is worth dwelling on because it is genuinely astonishing once you see it. The gravitational force between 2 protons is about 10 to the power of 36 times weaker than the electromagnetic force between them. That's not a rounding error. That's a factor of a trillion, trillion, trillion. A small magnet on your refrigerator can hold itself against the gravitational pull of the entire Earth. That's how weak gravity is. And we do not know why. We do not know why gravity is so weak, why it has the strength it has, or whether a universe with different gravitational constants would be stable, or allow stars to form, or allow chemistry to occur, or allow beings like us to exist to ask the question. There is a class of argument, I want to be careful here, because it can be misused, called the anthropic principle in its various forms, which notes that we can only observe a universe consistent with our own existence. If gravity were much stronger, stars would burn through their fuel in thousands of years instead of billions, and there would be no time for biological complexity to evolve. If it were much weaker, matter might never have condensed into stars and galaxies in the first place. The universe we observe is one in which the constants are compatible with our being here to observe it. That's not a coincidence, it's a selection effect. But it's not an explanation either. It doesn't tell us why the constants have these values, only that if they didn't, we wouldn't be asking. And that is where I want to leave you. Not with a tidy answer, but with a real question underneath the thought experiment. We asked, what if gravity disappeared for 5 seconds? And the physics tells us catastrophe on a planetary scale in the first 5 seconds of the return. But the deeper question the thought experiment is probing is this. Why is there gravity at all? Why does mass curve space-time? What is the actual underlying mechanism, the quantum mechanism that produces the phenomenon we call gravity? And if we changed it, if some intelligence or some physical process could alter the fundamental constants, what would remain recognizable as a universe? I don't know. Nobody does. And I find that not comforting, not reassuring, not an invitation to speculation about things beyond physics. I find it the most interesting fact about our situation. We live inside a physical reality that we did not choose and do not fully understand, governed by laws whose origin is unknown, held to the surface of a planet by a force that we can describe with extraordinary precision and whose ultimate nature remains, at the deepest level, mysterious. We built civilization on top of gravity. We evolved to navigate it. We use it every second of every day without thinking about it, and we still don't know what it is. That should not make you feel small. It should make you feel alive. Because the universe is not finished with us yet, and we are not finished with it. The questions are real, the stakes are real, and the work, the hard, beautiful, infuriating work of actually figuring this out is still going on. In labs and on chalkboards and in the quiet middle of the night when you can't sleep and you can't stop thinking about why a proton falls toward the Earth, that's where physics lives, not in the answers. In the falling,